8.7, we get to talk about the beautiful, beautiful number e. Just love this chapter. Here is our compound interest formula, where p is your starting amount of money, this is the growth rate, and then this is how long it compounds for. We know that n in particular stands for the number of times you compound over a given period, usually within years. I want to explore what happens with this as n increases. We're going to make this number of compounding increase over and over. So this p value I'm going to ignore. I don't want to worry about the starting amount. I'm going to turn this into 1 plus 1 over n to the n. That's all I want to deal with. I don't want to worry about the interest rate or the time. Let's just talk about what happens as n increases and nothing else. Well, if n is increasing, two interesting things kind of happen here. As n increases, this fraction gets smaller. Because if n is 2, you have a half. And if n is 3, you have a third. And if n is 10, you have a tenth. So the fraction keeps on decreasing, but this power gets bigger. So this fraction ends up getting closer and closer and closer to 0 as n gets really, really big. And this power ends up getting closer and closer and closer to infinity as n gets really, really big. And we basically have two things fighting. What happens when something shrinks really fast, but something else grows really fast, and they compete with each other? So as this gets closer and closer to 0, this basically becomes 1. It gets closer and closer to 1, but it's never actually 1, being brought to a really high power. And we'll explore what happens there. So if I have n equal 1, that's 1 plus 1 over 1 to the 1, which is 1 plus 1, which is 2. And if I have n equal 2, that's 1 plus 1 over 2 to the second, which is 1.5 squared, which is 2.25. So it's increasing. And if I have n equal 3, that's 1 plus 1 over 3 to the third, which is 1.3 repeating to the third, 1.3 repeating to the third, 2.37. So the value is increasing, but it's increasing by less each time. I mean, this went up 0.25, this went up 0.12. If I do one more, it'll increase by less and less, and now I'll start showing this on my calculator a little bit faster. In my y equals menu, I've made this equation, 1 plus 1 over x to the x, which is really just this right here, which is now gotten circled and written on a million times. And if I pull up my table, I can start entering values into my table. So I'm going to set this to auto. Well, here's, I'm way high. My table start at 1. Here's 1, which we just did. If the n value is 1, if the n value is 2, and the n value is 3, those are covered. And as you can see, as the n value increases, this value, this total, keeps on increasing, but it starts to increase by less and less. 2.65 happens 1, 2, 3, 4, 5 times, 4 times. 2.66 happens 5 times. 2.67 happens 7 times. And the amount that it increases just keeps on getting smaller and smaller. Now my n value is up to 75, and it's 2.7004, which was only 0.0003 above when n was 74. So I'll start plugging in some bigger numbers now. I'll change this to ask. We plugged in 75. Let's plug in n, or in this case x, equals 100. It's 2.704. I'll plug in 1,000. Oh, sorry, I typed in 10,000, but whatever, let's do it. 2.7181. So it barely increased. If I type in a whole bunch of zeros, well, like that, 2.7183. And it's eventually going to stop increasing. It eventually hits this limit where it doesn't go above a certain point. And so what we're talking about now, like if n equals 10,000 or 100,000 or even a million, here's a million. If n equals a million, that means we're calculating the interest, we're compounding the interest 1,000,000 times in a year. And that's more than once every second. I think that's more than 5 times every second. It's practically calculating interest every single passing moment. That's called continuously compounded interest. Continuously compounded interest is when you calculate interest every single passing instant. And it's really not just for interest on money, it's really called continuous growth. Anything that grows continuously has this sort of dynamic to it. And so this number that we had,
Ben Hakala to the front office, please. Ben Hakala to the front office.
the number 1 plus 1 over n to the n, as n gets really, really big, like as n gets really, really close to infinity. Basically, it isn't really possible, but if we had 1 plus 1 over infinity to the infinity, this equals 2.1878288. I want to make sure that's right. That feels a little bit wrong right now. It equals a special number. And the number is so special and so important that we give it its own letter. We call it E. And the number E is 2.71828. That's a little bit off. 2.71828. And it goes on forever and ever and ever. So E, whenever you see the letter E in a math class from here on out, that means the number E, which is 2.71828. Just like how pi is a number, 3.14159. E and pi are letters. Pi is a Greek letter, E is an English letter. Letters that we use to signify these important numbers. E is a number, it's called the natural exponent. It's part of why it's called the Euler number. This name here is Euler, looks like Euler. A dude named Euler discovered it in Switzerland. Much like the number pi, it has a decimal that goes on forever and ever without repeating, and much like pi, it is absurdly useful and important. In fact, E, the number E, is so important, we gave it its own logarithm. Just like how when you have a plain old log, it means log base 10. If you ever see an ln, it means log base E. So here, this log 100 is really log base 10 of 100. Log base 10 of 100 is 2. If you ever see an ln, if you'd like to, you could replace it with log base E, remembering that E is a number, a specific number, not a variable, not an unknown, but a specific number, 2.71828. ln, this ln up here, is called the natural log. It's a log of base E, and it's called the natural log because it appears in nature all over the place. E and ln just pop up all the time when you're dealing with nature, because in nature, things don't grow in chunks like every month or every day. They grow all the time. There's always bacteria splitting, making more bacteria, and there's always this growth taking place. So here's some simplifying that we can do. Everything that we do with E is just like everything else we've done with logs. Nothing changes. To convert this into log form, right now this is in exponential form. To convert to log form, I would do log base E of 20.08 equals 3, but we actually just call that ln. Log base E is really ln of 20.08. And you'll notice if I type into my calculator the ln button, which is right beneath the log button, if I do the natural log of 20.08, I get 3. I had to round a little bit, but it's 3. That's because E to the third is 20.0855. Natural log of 15 equals 2.71. Whenever you see ln for natural log, you know there's an E down there. So in log or in exponential form, E to the 2.71 equals 15. And just convince you that's true, second ln pulls up your E to the 2.71, 15. Okay, I can evaluate now. That just means calculate. So I can calculate the natural log of E to the fifth. Now, if you want to take a second and pause and think about what the natural log of E to the fifth would actually equal, that is really worth doing. Because you might be surprised to find that it's actually just 5. The natural log of E to the fifth is 5. Why is that? Well, think about it, because we don't know what this equals. So think about the circle thing. My base is E. I know that E to the x is going to equal E to the fifth. So that means that x must equal 5. And so over here, my base is E. E to the x equals -2. So x equals -2. And here the natural log of E is just 1. So it's like the power there. So natural log is kind of like the inverse of e, because e is the natural exponent, and natural log is the natural log, and logs are inverses of exponents. So the idea is ln of e to any power equals that power, because the base is e. I can also do some solving. If e to the x equals 400, I take a natural log of both sides. Natural log of e to the x equals natural log of 400. The x comes out in front, so x times the natural log of e equals the natural log of 400. But the natural log of e I know is 1. Just to convince you, I'll do it now, but this is the best thing about this. The natural log of e to the first is 1. The natural log just basically undoes the e. Then we get that x equals ln 400. That's something we could calculate if we were so inclined. The natural log of 400 is 6. 2e to the negative 3 plus 1 equals 5. Well, this doesn't actually have a variable in it anywhere, so I don't really know what I was going to have you solve. Maybe I meant to have a variable somewhere. Let's just make sure that's actually true, just to see if we're okay. If I have 2e to the negative 3 plus 1, yeah, I don't get out 5, so I don't really know what happened there. I think one of these is supposed to be an x. So let's make this an x. Let's say 2e to the x plus 1 equals 5. There's some number for which that's true. If I want to solve this, I want to get the x by itself. First I subtract the 1, so 2e to the x equals 4. Then divide everything by 2, and e to the x equals 2. Now to get this out of exponential form, I can put it in log form. Natural log, so log base e, really, of 2 equals x. So I do ln 2. And that's 0.69. E of x is about 0.69. One more, if the natural log of x equals 3, that means that e to the third equals x. So I just calculate e to the third. Now I get that this is probably weird for you, doing all this stuff with these letters, like it's just nobody's business. 20.08, we've already done that one, haven't we? But you just have to get familiar and comfortable with the idea that e represents a specific number, and you can do everything you want with it. And just like how log base 10 of 10 is 1, and log base 3 of 3 is 1, well, log base e of e is 1. And that'll cover everything for you. I think that's our day. Yeah, we're going to skip that. Great. Have a good, I don't know, life.